In this video we're going to recap what we already know about the effect of temperature on rate and then link that to how must temperature be affecting the rate constant K. So from the first year we knew that the rate of reaction will always increase when temperature is increased. We know that because when we increase the temperature we're giving the particles more energy, therefore more of them have energy greater than or equal to the activation energy, and there are more successful collisions, and we wrote this down in the first video of this section. Can you remember how to explain that using a Maxwell-Boltzmann distribution? So pause the video and see if you can sketch the shape of a Maxwell-Boltzmann distribution at two different temperatures and use it to explain why temperature has that effect on rate. So pause the video now and see if you can manage to do that. So there we go, you should have something like this where we're looking for some key features in our drawing. Remember the key features of the Maxwell-Boltzmann distribution. So have you labelled the axes? Remember it's a distribution curve, it's like a curve that's drawn over the top of lots of little bar charts. And so we've got the number of particles that have every particular energy up the side and the energies across the bottom. So the key features, it must start at the origin. 0 particles have 0 energy. The peaks must be skewed to the left. It's not a normal distribution, it's not evenly spaced out. Particles are much more likely to have the lower energies. Okay, so it's skewed to the left. It must come down close to the x-axis towards the end, but not touch the x-axis at the end. There's no maximum energy for particles, so it comes and runs in a line parallel to the x-axis towards the bottom. And then our second higher temperature, we're looking for the peak to be lower. So if you have a look at mine here, we've got the peak here for the first temperature, and then it's lower down here for the second temperature. And it's to the right, but once it's come lower down there, you can see that it always stays above the original curve after that, so that when we get to that shaded area at the end representing all the particles that can react, so all the particles that have energy greater than the activation energy, we can see that that shaded area is increasing at the higher temperature. And then we've written our little statement, many more particles have energy greater than or equal to the activation energy, so many more collisions are successful. And we wrote that down at the beginning of this section of work. So that is how temperature affects rate. How does that then link to how temperature could affect the rate constant K? So if we have a look, we know that rate equations take the form rate equals K to some power, the order, for A, times by the concentration of B to some order. Now, in an experiment where you would keep the concentrations of A and B constant and increase the temperature, if A and B are being constant but we know that rate is increasing, then it must be K that increases as rate increases. Now think back to the first year, you did a required practical on this topic. You measured the time taken for a cross to disappear underneath a reaction, so it was a disappearing cross experiment. You did that at lots of different temperatures and you plotted a graph of rate, which to find rate you did 1 over time against the different temperatures. Now that since A and B are going to be constant, so this is a constant, the concentration, and this is a constant, what we can say is that rate is going to be proportional to K, because if the other two are constants, then whatever happens to rate is going to happen to K. And remember, in chemistry the only thing that can affect constants is temperature. So although we're calling that the rate constant, it's only constant at a temperature, and once we change the temperature we change K. Can you remember what the graph looked like when you plotted rate up the side, but this time we're going to plot K, which is proportional to rate, so the graph's going to have exactly the same shape, against temperature. Now we're going to measure temperature in Kelvin here so that it does hit the origin. If we didn't measure temperature in Kelvin, then it wouldn't hit the origin because 0 degrees C is not 0 temperature. Can you remember what that graph looked like? It's an exponential curve. It's increasing exponentially, so it's going up like that. Now, if you've forgotten about that required practical, it might be worth going back to your first year work, having a look through the section on the required practical, watch the video about that required practical, and make sure you become familiar with it. The shape of this graph is quite important from that practical. In the next video, we're going to move on to mathematically explaining this connection between temperature and the rate constant K using something described called the Arrhenius equation. So we're going to be moving on in a separate video because it's going to take us a little bit of time to have a look at this equation and put it together. It's an exponential relationship, so we're going to be using a new function on our calculator.